Hello and welcome to another webinar for technology investors from ARM. Today we're going to be talking about some new technologies that will soon appear in ARM-based devices. And as many of you know, machine learning and artificial intelligence applications are widely deployed in ARM-based devices today, and we expect to see these types of computing workload being used more and more in the future. I'm joined here by two people who have a strong interest in the rise of AI and the impact it's having on the semiconductor industry. So dialing in from Austin is Nandan Nayampally, General Manager of ARM's Compute Products Group. And over from London, we have Gareth Jenkins, Managing Director of Technology Research at UBS. In a moment, Nandan is going to run through a few slides about ARM's latest technology for CPUs and explain how artificial intelligence is driving ARM's roadmap. But before that, let's hear quickly from Gareth. So Gareth, could you tell us why artificial intelligence is of such great interest to investors at the moment?
Yeah, thanks, Phil. Yeah, I can. And I would say that the real reason for it is that it touches on so many different end sectors across UBS's coverage universe and across the coverage universe of stocks for investors as well. In terms of the three areas, I would say the first is the short-term benefit both to the consumer but also to hardware and software companies potentially. Obviously, we've all seen the Amazon Echo box come through, personalized video, personalized search, etc. But as we move from narrowly defined AI to more generic AI, there are some interesting medium-term benefits that are being discussed as well. Autonomous driving has implications across the auto sector. Robotic surgery has the potential to be interesting across the healthcare sector. And so it's really the addressing of so many different subsectors that makes AI and machine learning so interesting. And then also there's the longer term social and economic policy implications around the potential for job disruption. There's been various comments made from the World Economic Forum to Mark Carney around job reduction potential from AI, and the policy and economic response to that will also be very interesting, I think, from an investor perspective. So with that, I will hand off and I look forward to some questions a bit later with Nandan. But first, his presentation. Thank you, Nandan.
Thank you, Gareth. Appreciate you hosting the session. So quickly, I joined ARM almost to the day 13 years ago, and so I look forward to actually this being the lucky 13. The last 13 years have been great, and we're looking at a very exciting set of things to come in the next few. So in that time, in fact, since I joined, at that point, ARM, the ARM926, the venerable ARM926 was in what we'd call feature phones. But since then, over the last decade, ARM and the partnership and the broader ecosystem has made a pretty drastic change to the compute landscape. And today, over 3.5 billion people use ARM-based devices as primary compute. Quite a lot of them do not have other means of compute, and most of the compute is done on these mobile, traditionally mobile or consumer devices. And I won't even go back to 2004, but since 2009 itself, the amount of just CPU compute in that device has gone up over 2 orders of magnitude, over 100x. And what ARM processors have done alongside other IP from ARM, as well as key system-on-chip development, platform development from our partners, is to take compute everywhere and actually democratize that, innovate more, such that ARM processors now are literally in every part from the very end of the sensor phase all the way to the cloud. And this has naturally been kind of the basis of not just broader compute. It's not just the basis of a lot of what is becoming a part of IoT, but it is setting us up for the next generation of smarter devices. Now, as we talk about these smarter devices, we kind of look at what is it that makes them smarter and better. And this is, again, when we get to the machine learning and AI side, the critical thing we want to get there is solutions are not about discrete CPUs, discrete GPUs, discrete DSPs. Really, the value that has come and the changes that have come in the industry over the last decade and a half have been more about system on a chip. And these are the ones that are funding very heterogeneous, optimized, collaborative compute engines. And if you look at a system on a chip, obviously the main processor is a key component. It runs the operating system, applications, a user interface, and controls most of the activities going forward. The graphics, or what you would call more data plane class processors that are doing more parallelized activities, would do very well with media and similar parallelizable workloads. You look around this system on a chip for other hardware controllers that control sensors, display, radios, and even on-chip and off-chip transactions, whether they be to memory or to other I/O. And then increasingly, there are accelerators. So you could see that in the DSP side, or now specialized accelerators for neural nets, for machine learning, image processing, etc. And usually, you also have the key components that you need to add on, specialized components like security that align with it. But all of these need to work in cohesion to deliver the best possible performance, the best possible feature set and capability in the best budget possible, whether it be silicon, power, or cost. And this is really where a lot of the change in the industry has gone, is intelligence multiplies when it's untethered rather than big kind of large boxes that you can't carry around. So with that said, if we look ahead to 2020, you're already seeing these devices going this way, but you would effectively have ubiquitous AI. I mean, my phone today already tells me at 8 a.m. what my traffic to work is, assuming that I'm going to work, right? So that's already there, but you'd see a lot more in all the kinds of devices out there. As you start getting more autonomous and as you start getting more reliant on these devices, safety becomes critical, right? And reliability becomes critical, whether it be in robotic factories, whether it be in more autonomous or driver assistance, and certainly more so in a lot of medical industrial professions as well. We're talking about mixed reality here. You can look at it as augmented. Mixed is a bit more interactive than that. We see that becoming more of a reality. And then at the end, all of this has to be delivered with a great deal of efficiency, because the level of compute is going up, but the form factors and effectively thermal footprints, cost footprints are having to be maintained or improved. So these have to be hyper efficient. As we talk about a fully connected smart world, you also need to make sure that you have a very secure private computing capability. So putting it all together, we do require a new approach, effectively not just to CPU design, but to system design. But we do look at a key component that we need to bring this together. And that, to us, is ARM Dynamic. It's a mechanism to redefine multi-core. It is an ability to pull together very different CPUs into the single cluster and operate them very efficiently and differently. So it gives you much greater flexibility to do right processing level for the right task. We're redesigning the memory subsystems so that the interactions, not just between the CPUs, but the rest of the system on a chip, is that much more efficient, performant, and low latency. And then we're bringing in the advanced compute capabilities. Is how does it connect well to the rest of the components on the chip? How do those interactions get better? And how do you actually deliver a much more heterogeneous, fully coherent intelligent system. So with Dynamic in place, right, what we expect, this is effectively a platform for the next few generations of ARM CPUs. It'll continue to obviously get further and further optimized and revised with them. We're talking about pulling the CPU and subsystem together, and that is, to us, the crux of what will enable the next level of machine learning towards more a broader artificial intelligence. Now, to aid that, we're talking about 50 times the AI performance on specialized AI types workloads just from the CPU itself coming in, and this comes through more specialized instructions, more optimized libraries. But more importantly, we're also reducing the latency and interaction to the acceleration, which will be on die. And those specialized accelerators will bring in a substantially higher amount of compute as well. So don't look at 50 times AI on the CPU as the limiting factor for the total system on a chip delivered. It's just a baseline. There's a lot more alongside that that will be enabled with Dynamic. So with performance kind of put in place, let's look at what does Dynamic do in terms of enabling these things to work together. So the single cluster design is very useful for optimizing the right level of processing for the right task. And this is critically important in delivering the most efficient performance possible, but as well as the performance is ready when you need it. By putting all of these into a single cluster, you're increasing the efficiency of both shared data as well as transactions when they move from one processor to the other, being a lot quicker through faster task migrations. And some of these examples will kind of highlight it for you. So if you look at it, the voice recognition, before we got there, most of the tasks that we run can be run on the little CPUs. Going with voice recognition, it jumped to the big CPU for a little bit, very seamlessly, completely transparent to the application itself. It's just a processing resource underneath. Now, if you go back to steady state where you're doing all the bookkeeping, OS, user interfaces, etc., you then get, let's say, you're coming across an interrupt and you say, there's a face to recognize. I'm trying to understand whether this is the right person for security or otherwise. Face recognition would again move the tasks initially to the bigger CPUs because there's a large amount of computation to be done. And once the key algorithms are set up, you come back to steady state. It's been identified, and you relax back to the little CPUs. And all of this, again, handles seamlessly underneath using the same mechanisms that we had for big. LITTLE technology before. Now, moving on, what that means is that if you pull it all together, if you look at the history of it, a decade ago, we launched our first multi-core processors that put 4 CPUs into a single cluster. They were all very similar types of CPUs. They had to be either turned off or taken up and down together. About 5 years ago, we introduced Big. LITTLE, which could mix and match to different types of CPUs, but again, they were defined within their cluster. It served the mobile industry extremely well by giving an extremely large dynamic range of performance while maintaining battery life, while maintaining thermal aspects in a small form factor. Now, Dynamic takes it to the next level and enables within this single cluster design not just all the cases that we've used before, but a lot more interesting use cases. So you could actually start seeing smaller form factor phones with just one large CPU and a larger number of small CPUs. Now, all those types of combinations also become possible, so really enabling a lot more compute in a lot more different form factors. So a lot more flexibility for us. And then when you put these into devices or systems that need a greater level of safety and reliability, dynamic becomes the basis of providing the next level of safety compliance. So in the automotive world, the ASIL-D is the highest level of safety critical operation, and it helps you recover from faults. It helps you recover from destructive use cases and partition off processes that would have potentially cratered systems. So Dynamic offers, it's designed from scratch to understand these mechanisms, the design flow, design process, monitoring, checkpointing have been developed for it. The mechanisms that you need to support a safety critical standard are built into Dynamic, along with what we can do with the CPUs on top. And naturally, the faster responsiveness that we've built into the system helps even more, especially for safety critical applications and faster decision making. So this will really open up stronger adaptive computation systems for ADAS, which is kind of the stepping stone towards autonomous driving and autonomous vehicles. So to summarize, Dynamic is kind of a new paradigm for compute that we have put together. It's a very versatile technology that allows you to design very flexible, very differentiated systems. It brings in smarter capabilities for artificial intelligence and machine learning, both from the CPUs that'll be plugging into them in short order, but also how the rest of the other compute engines can plug into it. It will boost the performance that you need for these kinds of applications, along with the efficiency, and it is very scalable into very different markets, as we said, from chip to cloud. So all of this tied together with the trust zone technology, which kind of runs through Dynamic, makes it what we believe is the right stepping stone for AI in 2020. Well, we look at it as this will be ubiquitous by that time. These are points that we will see along the way with Dynamic technology as well. So with that, I will hand over to Gareth for the Q&A part of the discussion.
That's great. Thanks, Nandan. I thought I might start with a very, I guess, somewhat easier question in terms of just setting the tone for some of the generalists that might be listening. And I wondered if you could just maybe talk a definitional difference between machine learning and artificial intelligence, how you see those being distinctly different from ARM's perspective.
Yeah, I think that's a great starting point, and I'll try to keep it as simple as I can, right? I mean, because there is a lot of nuance to it. But as a broader topic, artificial intelligence is a broader concept that will pull together machines, systems, in order to carry out tasks that we would consider intelligent, right? So these are systems that can work together collaboratively to do smart or intelligent tasks. Whereas machine learning, to me, is a subcomponent of that, and it's one application of what AI will need as a whole, and it's built around how can we feed machines data and algorithms and let them learn for themselves.
That's great. And so now maybe digging into a bit more around ARM's efforts in this area. I mean, you described some of the dynamic benefits and the 10 to 50 times performance improvement. What are the most important elements within that 10 to 50 times performance improvement? Is it the memory power management? Is it the power state transitioning? Is it putting AI accelerators directly onto silicon? Is it the processor instruction library? What are the kind of the very key issues that at play in that performance improvement?
Now, I think that's a good question you ask, because it needs to be clarified clearly. obviously, from an AI perspective, there's a lot of key components whether you want to address. What we talk about in terms of the 50 times improvement was specifically just the kinds of instructions that we're adding into the next generation CPUs. I mean, they haven't been announced yet, right? Which would do things like that help with, 16-bit floating point, matrix multiplies, and other compute components that are very useful for artificial intelligence and machine learning that help with, convolutional filtering, etc. So this is independent of anything that needs to be done outside of the CPU. Now, to be fair, this will also mean that we are optimizing libraries that will sit to deliver this kind of 50 times improvement, right? And this is just comparing the kinds of algorithms that you can run on a smartphone class processor today and saying, in a smartphone class processor 2 to 3 years from now, in that system itself, you'd get nearly 50 times as much performance just from the CPU itself for AI type workloads. Now, if you add in, specialized acceleration and working closely with the CPU, then you're actually seeing multipliers beyond that in terms of the overall system on a chip output for it. Does that make sense?
Yeah, absolutely. That's very clear. And you kind of touched on this, that there's, obviously not silicon yet, but what's the timetable for Dynamic being adopted on silicon by partners? And you sort of touched on smartphones briefly, but would that be the first use case that you see?
Yeah, I think naturally for ARM, the smartphone is generally the first line of entry, but also if you look at the innovation, there's a huge amount of innovation on AI ML happening on smartphones, primarily because it's a platform that a lot of people understand, and it's a platform that is easily accessible, and you can get users to test it very quickly, right? And you can use it, the sensors on board, all of those come standard for most smartphone platforms. You can use that to build better machine learning or AI systems. So we see that there. And the one thing I would add is, we talked about the 50 times improvement on the CPU and a much larger improvement as a combination of CPU plus acceleration, etc. This is also where a lot of ARM IP sits, right? So you look at GPU contributing to it. You look at vision engines, DSP engines all contributing to it. All of that comes together quite easily in smartphone platforms, right? So we see that showing up first in smartphones, and it'll probably go into a lot of consumer devices, but also further up and down the infrastructure in the next couple of years. So if I were to effectively understand your next question, which is when is Dynamic expected to hit the market? We have been working on this technology with partners for a while. We haven't made any announcements yet, but you will expect to see Dynamic-based devices in the market in 2018.
Wow, okay, so 2018 for devices, and then for infrastructure maybe a little bit after that, presumably.
Yes, that's probably a fair analysis.
And you mentioned this, but there's basically an unlimited potential for designs of various clusters, 1+7, sort of various almost big little type structures. Do you expect one architecture implementation to be favored in the sort of initial phase of adoption? I mean, is there a preferred architecture that you're seeing partners work towards?
No, I think one of the key benefits of the ARM ecosystem and the ARM technology platform is that people design configurations to fit specific markets, and those don't always last forever either, right? So you have the octa-core configurations that premium devices still take, but you suddenly saw a large number of mid-range devices that used 2+2 2+4 or 2+6 systems. And we start seeing, as the mid-range and lower-end devices demand more capability, you could start seeing 1+4 or 1+7 even type systems that you could see in the marketplace. And the advantage of ARM being portable IP is that dynamic-based platforms could be seen in 28 nanometer, could be in 16 nanometer, 10 nanometer, and 7 nanometer. Certainly the avant-garde platforms or the leading-edge platforms will probably go to 10 and 7 in the near future. The other ones could actually stay and still provide the benefits of the technology itself.
And is there any benefit to using a kind of physical IP design set from ARM as well? I remember with Big. LITTLE there was a kind of wave of silicon partners that came on using both the ARM POP as well as Big. LITTLE implementations. Would there be a benefit to using the sort of POP package from ARM?
I think that I'd be lying if I didn't say yes. I think it's an absolute necessity in some cases, especially when you're trying to squeeze out the maximum amount of performance for the, in terms of efficiency, right? So the POP physical IP gives you the ability to push to the maximum you can get of the capability that the process technology gives you. And they've been designed in conjunction with the CPUs, so naturally are very tuned for them. The other big thing that the POPs actually help you do is reduce your risk of achieving those tasks or actually getting to market with a good yielding part, right? Because finally, a lot of the dollars are made in making sure that your yields are high. So the POPs are designed to help you get to market faster, get to the charter performance, power, and footprint goals that you're trying to hit, and get you the best yield possible.
That's great. And it feels like the emphasis is very much on Cortex-A and sort of some of the heavier workloads around the smartphone and maybe infrastructure over time. But many, I guess, AI and ML applications involve a lot of embedded functionality. So just wonder what the rationale behind not integrating with Cortex-M is, or whether there is integration, and I may not have seen it, and whether that will come at some later date.
That's a fair question, right? And I think what we kind of discussed in the beginning of this around the system on chip is these are complex systems. While Cortex-A and Cortex-M have a common architecture, usually the programming paradigms are a bit different, right? Cortex-A is designed much more for higher-end compute, higher-level operating systems, UIs, etc. Cortex-Ms are truly designed for optimizing interrupt response, helping with connectivity in that regard, co-processing around it. So you are right in that they could be integrated together, but what we see are these Cortex-Ms will probably be control processors within, let's say, an array of AI accelerators, right? So they may be actually doing the bookkeeping, the management of data along there. So I would think of it as not that we need to integrate them into dynamic, but systems of acceleration that will integrate Cortex-Ms, and those will plug into dynamic. So we still have the flexibility that our partners continually use to replace, in fact, some cases, specialized computing or finite state machines into technology that Cortex-M provides. So on the other end of the spectrum, I'll just say, I think this is also a very good point you raise, is on IoT endpoints, again, those will start getting more and more intelligent as well. You can actually run lower grade ML algorithms or kind of lower end vision algorithms on Cortex-Ms as well, right? So in devices that are very, very constrained, you will see those being used as the first line of defense or first line of recognition as well. So I know we're concentrating on Cortex-A at this particular time on dynamic, but if you look at the bigger picture, there are ways to, there are actually constant use cases around which Cortex-M is playing into this overall AI landscape.
Okay, that's very clear. And at the other end of the spectrum, I guess with core link and with this sort of high core count multi-cluster systems, dynamic can handle infrastructure markets potentially, but how does this play out, and what are the kind of use cases in the infrastructure market for dynamic?
Again, this is a fair question. So dynamic itself allows you, just as you have acceleration in AI space, right? There's acceleration that is needed for communications algorithms, for encryption algorithms, for deep packet inspection, etc., in the infrastructure space, right? So the fact that we talked about very low latency aspects to connect into the CPU cluster locally help in the infrastructure space as well. As you also mentioned, with Core Link, you can take these dynamic clusters and enlarge the system as well. So we talk about 8 processors in a cluster today, right, for dynamic, but with Core Link, this could become a 16, 32, 48 processor system or larger. So you still get a lot more density of compute. The way dynamic is designed, that means on-chip throughput is enhanced for these types of systems, which is again very critical. And so you could see these actually being built into intelligent cloud infrastructure, which are combining some of the networking and cloud functionality, or being more cloud or being more networking. And to say how this works overall, you think whether you do it at the back end or the front end, ARM-based systems are already working in HPC context, right? And we talked about our libraries for the numerical algorithms group and BLAS, etc., that are tuned to ARM. You would similarly see TensorFlow. We've talked about TensorFlow type of algorithms being tuned to ARM. And if you look at what Azure does, these types of, over half their workloads are suitable for being run on ARM. So dynamic as a platform, but more importantly, the compute capability, the libraries and ecosystem are making it possible for us to play a much stronger piece in the infrastructure part for the AI market.
Very clear. Okay, and there's clearly a lot of interest in this area from the States. I wondered whether you can talk a little bit about differentiation versus x86. Intel's taken a bunch of steps in AI around its Nirvana platform. It also lays claim to 100x improvement in terms of performance by 2020. And I think its EMIB platform is quite interesting as it enables monolithic integration on a sort of non-monolithic integration across products. When you talk about a 50x performance improvement, how does that compare with Intel's 100? Are we comparing apples to apples on this one?
Yeah, I think that's a great starting point to discuss, which is, one, we don't know the starting point, right? So from what we talk about here, we're saying the kinds of algorithms you run today on a smartphone class platform, you'll see F50x. Now, if you expand that smartphone platform into an infrastructure platform based on ARM processors, again, you'll see the scaling as well, right? Now, the other thing I don't know is whether the 100x is talked about as SoC, right, capability, or system capability, etc. Whereas what we're talking about on the 50x, as I said earlier, is purely what is done on the CPU. When you add in the acceleration around that and the closer connection, coherent connection with that, it's actually a multiplier well beyond that, right? So when we talk about 50x, it's a very limited portion that we're talking about improving. The overall system will be much higher in terms of delivery. The other thing I would say is coming back to the system on a chip, when you talk about transactions on die, even to larger parts of the, that are far away on the die, you're talking about tens to maybe hundreds of cycles, right? Worst case. Whereas once you go off die, no matter what, even with EMIB type things, you're talking thousands of cycles, if not more, right? So when you start considering that, there's a lot of efficiency lost going between die than there is staying on the same die. So there will be obviously other accretive benefits of putting these components closer together in conjunction. So from our standpoint, dedicated accelerators close to the CPU, connected coherently with a very low latency transaction base really gives, in our view, a much bigger bang for buck that we haven't yet even quantified.
Interesting. Okay. And again, we kind of touched on this with interaction with other elements in a wider system, but how do you see the role of GPU in a kind of artificial intelligence, machine learning environment? I think NVIDIA's Xavier is 8 ARM cores and 512 CUDA cores. So I just wondered how you see GPU playing out.
So I think it's fair to say, right, for parallelized workloads where AI does have inherently a lot of workloads have parallelism, GPU has a role to play. But I would question the notion of being GPU is an AI system. Naturally, I'm a CPU bias, so take my words with a grain of salt. But to us, GPUs will play a component. Other accelerators, some DSP-style acceleration will play components. There are specialized neural net accelerators which are substantially more efficient than general-purpose GPUs in some of these cases, which will play a component. So this is going to be very workload dependent, and our belief is GPUs will have, because a lot of systems include GPUs will have a role to play. GPUs do play a good role in some of the HPC type workloads, but in broader AI, you will need CPU, and in fact, a very strong component of CPU and a lot of other acceleration to make this possible. And which is why ARM is generally invested. We do have GPU, again, efficient GPUs in there in our portfolio. We invested in Apical to look at vision systems, camera systems. We're looking at audio systems and other acceleration around it that can help you build a much more capable ML system or AI system of the future.
That's very clear. And I wanted to just come back to one of your slides around automotive. I think you could argue that the car is going to be one of the most advanced use cases for robotics and AI. What specific design features do you have in the ARM architecture that render this very suitable for automotive, and what makes DynamIQ-A SoC ready?
Yeah, that's a very good question, because the answer is not very simple, right? So part of it is, if you look at the specification, in this case the ISO 26262 specification, it puts in everything from how the specification was, requirements were captured, how the specification was built, how the components were designed to specification, how can we define faults, how can you recover for them, etc. So this is not just a one-step answer. It is, we had to change over the last 5 to 7 years our entire development process to incorporate these key checkpoints to make sure that you can design to something that is to that standard, right? So that's a first thing, is change in process itself. The second thing is how the recovery mechanisms, obviously error correction, etc. We did that a long time ago, but there are others that help you isolate robustness. So how does the virtualization aspect help isolate tasks from one to the other? what kind of recovery mechanisms that you need to put in. So those are all built into Dynamic as a platform and the CPUs that work alongside them. So, and then finally, the third component of that is certification and testing. So we usually go through third parties to ensure that we are complying with that. And also there's a software layer on top that looks at test and recovery. So we've had to go through various phases to achieve this, and we're doing this actually across our portfolio. And then within it, if you just look at some of the basic things, certainly responsiveness is always helpful for fast recovery. The checkpointing that can be built in, recovery debug mechanisms that can be used to recover from faults, etc. So there's a suite of things that we need to do right from how we capture the design to how we deliver it in the end.
Okay, and I guess there's a lot of questions around NVIDIA versus Intel in the car, but do you see other potential partners coming in the automotive compute arena for AI applications?
Absolutely, right. So I do think a lot of the key vendors that are in the automotive side are using ADAS platforms, right? So if you look at Renesas and the R-Car 3 platforms and going beyond that, NXP has platforms from its Freescale times. ST Microelectronics is talking about what they're doing there. So ARM has worked with a lot of these vendors for the last decade or so in the development of both our criteria for certification as well as the requirements for the products. And we do see also working then with the tier ones that feed into the automotive OEMs so that we are aligned with what is needed for the OEMs. So we do see that automotive is not a one-horse or two-horse race. It is a broader set of players that can bring to it. And when you look at ADAS and beyond, and automotive in general, it is also, you look at sense, perceive, decide, and actuate. If you look at a lot of the automotive vendors, they've always been in the actuate side, which is really where a lot of the safety critical parts are, and they have been moving into the perception and decision phases. So we do think this is a broader field.
Okay, very interesting. And it would be remiss of me not to ask a question around security. As we move towards a kind of more automated world, how does ARM's trust zone products fit into or fit with Dynamic in terms of providing security?
Yeah, I think whether it's IoT, whether it's AI, ML, I think the common issue is security. And so trust zone naturally forms a basis for it, but I think I need to step back a bit to say security is not going to be software only, right? So we all agree, I think, that that is the case longer term. The other thing I would say is security is as important in your Fitbit type device, activity tracker, as it is in your cloud infrastructure. So trust zone is this is why we kind of invested in trust zone for even the Cortex M's, because if there's no security in the little data, you have a problem with the big data as well. And we think security in hardware with Trust Zone Plus, actually a lot of the encryption capabilities that we've built both into processors as well as components that we've introduced. It's like the CryptoSeal part from ARM. Those are important along the chain all the way from the sensor to the cloud. And Dynamic plays a role in it because it'll be in consumer devices with a trust zone, with other add-on security in hardware. And the same thing can be extended into the cloud where this could be part of networking and server systems with not just trust zone as a baseline, but other accelerators built into silicon. So security is kind of engendered in the hardware itself to make it that much more compelling.
Okay, that's really interesting. And then I guess just last one from my side, which is, one on the development community more widely. One of the challenges that the dynamic type approach historically has had is the conflict between ease of use for developers versus maximizing performance and efficiency. And I just wondered how dynamic deals with developers and how involved is using dynamic for the developers themselves.
Yeah, that's an interesting question, and just like Big Little in some ways, dynamic should be transparent and invisible to the software programmer. So this is taken care of underneath the OS level, right? And we have been updating the Linux code that is already primed for dynamic hardware, both existing systems today, OS today, as well as the releases coming forward. They'll continue to optimize. Now, moving to how do you make this interesting for AI developers, the good news is that most of the things that we're talking about, the specialized instructions that we're putting in, and the other acceleration hardware that'll go into SoCs from different vendors, you'll have different things. Usually it will be hidden underneath an API. And from our standpoint, the optimizations that you need to make use of will already be built into our library. So about a couple of months ago, around the time we launched the Dynamic platform, we also launched our ARM compute libraries, right? So those were things that can be used to help accelerate neural nets, convolution filtering, etc. So you can use the standard development environments that you have today for smartphone or consumer or other platforms, which developers are very familiar with, and still make use of all the benefits that are emanating from the technology underneath. And we do think that there are multiple APIs that you can use. I mean, whether you use TensorFlow type API, OpenCV, the wit.ai or AI.api. So all of them will help you utilize from a software development environment ARM-based platforms or ARM partner platforms, maximize what you get out of it. And the optimization for power performance, if done right underneath, will already be there built in with common interfaces for the software developer. So I know I've kind of talked about it from a software developer standpoint first, but if I look further at the ecosystem, we're working closely to help a lot of our partners to build out their specialized solutions around the generic ARM platforms. And so you'll see a lot more systems on chip, if you haven't already seen, that'll come out with it. And then you basically see underneath all that, there's a lot of innovation, right? So if I went back to your first question about how are you using the elements well, there are so many different algorithms being used, and some SoCs and some development environments may be a bit more GPU-centric because there's a lot of parallelism that you can use to more GPUs. There may be specialized ones that have specialized acceleration, etc. But usually you'll see that the CPU is a common component which we can provide. So overall, we're trying to address it not just from technology hardware standpoint, but make it as easy for the software developers to build on it with the level of ubiquitous platforms they have. And so summarizing, I think, we think Dynamic is a very versatile compute technology with all the key capabilities for AI/ML, a huge amount of performance and efficiency boosts that you can get well over what you have today. And it is a very scalable technology that can be deployed across a lot of markets with that need reliability, intelligence, and security. So with that, I'll hand over to you, Gareth.
Great, thank you. All it remains for me to do is to say thanks very much, Nandan. Thank you very much, ARM, for allowing us to host this very, very interesting call with very interesting subject area, obviously, for investors and for ourselves. So thanks very much, and I think this will be available. Replays will be available on the ARM website and also on their YouTube channel in due course. Normally a period of time afterwards. Thank you very much, Nandan. Appreciate it.
And thanks, Gareth, likewise, for hosting this and a very interesting discussion here.